It's a great pleasure today to have Jaehan Bae as our guest. Jaehan comes from South Korea. He was born in Seoul, and he earned his bachelor and master degree in astronomy from Seoul National University in 2006 and 2008. After that, he worked at the Korea Astronomy and Space Science Institute for 3 years before moving to the University of Michigan in 2011, where he then got his PhD in 2017, working with Professor Lee Hartman and other people there. From 2017 to 2019, Jaehan was a Vera Rubin postdoctoral fellow at Carnegie Institution for Science. And since 2019, he has been a NASA Hubble Fellow in the SAGAM program, postdoctoral program, always at Carnegie Institution for Science. Jaehan is an expert, is a theoretician, is an expert on formation of planets and evolution of protoplanetary disks. And today he will tell us about, the title is Toward a More Complete Picture of Planet Formation. So with no further ado, one more thing. Actually, if you have question during the talk, if you have compelling question during the talk, raise your hand and I'll try to monitor that, or put your question in the chat. Otherwise, if your question can wait until the end, we would prefer to wait until the end of the talk, and where we will have a Q&A session. There is also, after the colloquium, we will stay online for this informal wine and cheese. So please stay online if you have also questions. Okay, so Jaehan, I pass the control to you. So feel free to start whenever you're ready.
Okay, great. Thank you so much, Andrea, for the introduction. Can you hear me okay?
Yes.
Okay, great. Yeah, thank you everyone for joining today. I have been really enjoying talking with many of you, and I'm looking forward to meeting more of you tomorrow. So the goal of my research is to better understand the planet formation processes. And today I'm going to tell you about how the field has been moving forward to better understand planet formation, and how I have been contributing, and how our future would look like. So here's the outline of my talk. I will start with an introduction, talking a little bit about history of planet formation and exoplanet studies, and some challenges that we have been facing. I'll then introduce some of the state-of-the-art observations of protoplanetary disks, which are the birthplaces of planets. And then I'll move on to discussing how planet disk interaction theories have been improved to reconcile these new observations. Then I'll present one specific example, PDS-70 system, and show you how theory and observation confront each other. To set the scene for everyone, here's an artist's impression of our Milky Way galaxy. The diameter of the galaxy is about 100,000 light years, or in astronomers' unit, it's about 30 kiloparsec, or 6 billion astronomical units, where 1 astronomical unit, or 1 AU, is the distance between the sun and the Earth. So the sun is located about halfway from the galaxy center to the outer edge. So the sun is here. And our galaxy is a spiral galaxy, and you can see here many spirals. And along the spirals is where most of the stars are forming. So if you zoom in one of the nearby star forming region, this is what it looks like. So this is a real image now of the famous Orion Nebula taken with the Hubble Space Telescope. So the size of this image is about 13 light year. So this entire region is literally less than a single pixel in this image on the left. So we are, we have moved quite a bit in terms of size. Now, if we zoom further into one of the dense regions in this Orion Nebula, this is what it might look like. So this is a cloud, a chunk of cloud of gas and dust. And when the interstellar gas is sufficiently compressed, which can happen actually under various situations, for example, the things, gas and dust can be turbulent, and the turbulent eddies can be dense enough. Or, as I said, we are spiral galaxy, within spiral galaxy. So spiral shock fronts, it can form dense regions. Or if there's supernova explosion nearby, the expanding shell of supernova can create some dense regions. So in such cases, the cloud can become very dense and start to collapse due to its own gravity, so self-gravity. And that's how stars form in a nutshell. But the collapse does not form just a single star because molecular clouds, they are not stationary in space, but they are moving around and rotating, and they have non-zero angular momentum. And the angular momentum has to be conserved during the collapse. Now, if you think about the size, right, the typical size of a cloud is about 0.1 parsec or 20,000 astronomical units, whereas the size of a star is usually, well, most of the time, less than 1% of an AU. So that's about 6 orders of magnitude difference in size. And we end up having a disk surrounding the star to conserve the angular momentum. So in some sense, protoplanetary disks, they are a remnant of star formation processes. Looking more closely to protoplanetary disks, this is what protoplanetary disks might look like. And here are a few aspects I'd like you to keep in mind during my talk. The first is that it's obvious, but protoplanetary disks are three-dimensional objects, although they can be pretty thin. And they consist of 99% of gas and 1% of solids, and that's in terms of mass. And this ratio is inherited from the molecular cloud they are forming. The third is that the most of the gas mass is in H2 hydrogen molecule, right? But they are very poor emitters at typical protoplanetary disk temperatures, which is about a few tens to a few hundred K, just because they don't have any dipole moment and they are in ground state at this low temperature. So if you wanted to look at the gas in protoplanetary disks, we cannot use H2. So we need some tracer molecules, and the most commonly used one is carbon dioxide, CO, and I'll show some images of CO observations later on in my talk. The next one is that grains have different spatial distribution, and that's as a function of their sizes, which is determined by a complex processes, as you can see here. So grains are subject to turbulence. They can also settle vertically due to the gravity. Also, they interact with the gas and feel aerodynamic drag. By the way, that is a function of grain size, as you can see from here. So different sizes of grains behave differently. And also they evolve in size. They can grow, but also they can fragment. So there are a lot of complex physics going on. But for this talk, for the purpose of this talk, what you want to remember is the small grains. When I say small, it's usually micrometer sized grains, very small grains. Those are very well mixed to gas. So if you look at this right side, small particles distribute pretty much the same as the gas in vertical direction as well as in radial direction. Whereas if you think about larger grains, like millimeter sized grains, centimeter sized grains, pebbles, right? They are quite different in terms of their distribution and behavior. Most importantly, you see that they are settled toward the middle plane. They tend to feel significant aerodynamic drag, and they tend to collect in pressure maximum. So that's one important thing. And the final thing I'd like to point out is that it is generally easier to observe emission from grains than gas. And that is because if you think about certain transition, for example, CO molecular transition, we know from quantum mechanics that there's certain transition energy or temperature that you need for each transition, right? So in that sense, we need very specific wavelengths or frequency we need to look if you were to look at certain gas transition. Whereas the thermal emission from grains, those are continuous, so we call it continuum, and you can use broadband to what's going on with dust. So in that sense, observing grains is easier than observing gas. Okay, so with that introduction, the big question I'm trying to answer through my research is how, when, and where do planets form? And you can think of a few different approaches to answer the question. Here I listed a few of them, which I'll go through one by one. The first is to use theories so solve equations with relevant physics in them. And if things become complicated or things become non-linear, then we can solve those equations using computer simulations. And here are two examples from two seminal papers from 1990s. The one on the left is a model trying to explain the formation of Jupiter going from solid core. So you see three curves. The one with noted with MZ, this one is the mass of the solid core. So you grow the solid core first with a mass of about 10 to 15 Earth mass, and then you start to create gas, hydrogen and helium gas, this one. But it's very slow, and that is because the solid core is still growing by accreting planetesimals in this model, and the accretion heat prevents a lot of gas cooling down on the surface of the planet. But at some point, as the planet accumulates more and more gas, it grows in mass, and then at some point it undergoes runaway accretion, and at that point, the core start to accrete a lot of gas like crazy and become a gas giant. That's one model. On the right-hand side is through gravitational instability. So this is massive enough and or cool enough, then you can trigger the gravitational instability and form clumps. And these clumps can become a planet, a giant planet. So that's another mechanism. Second way to tackle the problem is to infer the formation processes by looking at the end product. So when I say the end product, I mean mature planets that have completed their formation. So we have 8 such planets in our solar system, including the Earth we live on. So we can look at them closely. We can also send them satellites and probes to have a closer look. In addition, we have discovered more than 4,000 mature exoplanets, and those are planets orbiting around stars other than the sun. And we can use them to develop and test our hypothesis. So this is this diagram shows you a cumulative detections over time from starting from 1990s to 2021 this year. And you can see this exponential growth in number of the exoplanets we have discovered. And there are more than 2,000 additional exoplanet candidates right now. So I'm sure that the number will keep increasing in the future. And the different colors in this diagram show different techniques used to discover those exoplanets. And I'd like to highlight that over many decades, the field of exoplanet has come up with brilliant ideas to not only find exoplanets, but also quantify their physical properties. So I want to explain a little bit more detail of how to find mature exoplanets. These are two most successful ones, transit method and radial velocity method. So more than 90% of the total exoplanets discovered so far are discovered by either of these two mechanisms, these two techniques. So let me play this one. So transit. So the idea is simple. So you have a star and a planet, and if it happens such that the orbital plane is aligned to our line of sight, the planet will go across the stellar surface in line of sight. And when that happens, the starlight is blocked by the planet. So the flux we get is decreased, and you can infer the properties of the planets like size and how far the planet is from the center star. And in this case, radial velocity, there's a planet and a star, and because the mass of the planet is not 0, they have a common center of the mass, right? So the star is wobbling, and we are looking at the stellar spectrum and see certain atomic lines and see if they are red shifting or blue shifting. And by looking at them, you can infer that there might be a orbiting planet around those stars. Okay, sorry about that. So on this figure on the right side here, what I plotted here is the mass of the confirmed exoplanet on the y-axis in units of Jupiter masses in logarithmic scale. And on the x-axis, what I plotted here is the semi-major axis or orbital distance from the star in units of AU, also in logarithmic scale. And this is great. We have discovered a lot of planets, but one big caveat, though, is that we don't really have a direct answer to whether these planets have formed in situ at the location that we have discovered, or they have formed somewhere else and experienced significant orbital migration. For example, if you think about these hot Jupiters, right? This one, they have masses of about Jupiter masses, but they are located very close in, even closer than the Mercury to the center, our star, the sun. So the question is, if they have formed in situ there at 0.1 AU distance from their host stars, or they form further away like our Jupiter did, and they migrated inward, right? We don't have a complete answer to this just by looking at the current configuration. The third method I'd like to introduce is to observe planets while they are forming. This is, of course, so obvious. If you want to know something about formation process, right? The best way is to watch what happens while they're forming. But this has been extremely challenging for various reasons for planet formation. And unfortunately, the most successful exoplanet detection techniques with which we discovered more than 4,000 exoplanets so far cannot be applied to finding protoplanets. Okay, so what is the problem? Here's the first one. So the planets form relatively quickly. So on this diagram on the right, what is plotted here is the fraction of the stars in each star forming regions. For example, this one shows Taurus star forming region. And this plot shows the age on the x-axis, so about 1 million year for Taurus. And on the y-axis, the fraction of stars that has near infrared between 1 to 10 micrometer excess emission. So the idea behind this diagram is that if you have only a star, right, it's more or less a black body. So you expect to see, if you plot brightness as a function of wavelength, you would see this Planck function-like feature, spectral energy distribution. But when there's a disk surrounding the star, you'd see this excess emission coming from dust around the star. So if you count all those stars that has excess near infrared emission, then you can kind of guess how much percent of the stars in that star forming region still has a disk around them. So at the point they are about 3 million years old, 50% of disks are gone. And at about 10 million years old, almost all disks are gone. So what that means is that if you want to form planets, especially gas giants, they have to form during the time when there exists gas. So you need to form planets within 10 million years. And 10 million years, it's very short time scale, right? If you think about this process, you start to form the star, and you have this disk of gas and dust. And all this process, this part is only taking about 10 million years. And then the lifetime of the sun-like star is 10 billion years. So you have only 0.1% of the time during which time planets form around a star. So in that sense, planets form quick, or in other words, young stars are relatively rare compared with mature stars. The next is that young stars are generally located far from us. So the distance to the closest mature star, which is Proxima Centauri, is about 4 light years. On the other hand, the closest star forming region like Taurus or Ophiuchus, they are 400 light years away from us. So the number of photons we get from a star decreases over radius proportional to 1 over distance squared. So if you have one star at 4 light year and the other star at 400 light year, and assuming that their intrinsic brightness are the same, then means that we have 10,000 times smaller number of photons from the distant star, which would make it much harder to observe, or require much more observing time to obtain the same quality of data. So that's a problem. The third one is that the young stars are embedded in their birth cluster. This is again the image of Orion Nebula taken with HST, Hubble Space Telescope. And as you can see, there's quite a lot of nebulosity throughout the region and some extinctions as well. So if you think about how we find exoplanets around other stars, you need to clearly see the star to use either transit method or radial velocity method. And it is just impossible for these young stars embedded in their birth cloud. Along the same line, in addition to the nebula gas and dust, the disk surrounding the star can block the starlight. So this is an example of a star IM loop taken at 1.6 micrometer, so infrared wavelengths. What we are looking at here is the star is at the center, and star emits photons, right, stellar photons. And it is, if you look at this diagram, stellar photons are scattered off the surface by the small grains toward our line of sight. So we are looking at the upper surface, and here's the dark plane, and that's the midplane of the disk. And that is because stellar photons just cannot get through it because there's so much material there. And this bottom part here is pretty cool. This is backscattered starlight. So star emits photons, and it's scattered from the backside of the disk. So we are looking at the backside of the disk. So if you were to use transit method, you need to look from the sideways, right, on disk, and it's just simply impossible for these with these young optically thick disks. And finally, young stars are more active than mature stars. This is a cartoon showing what the inner part of a protoplanetary disk would look like. So here's a disk, and young stars have pretty strong magnetic fields, and the disk material would fall onto the star following those magnetic fields, and the accretion is variable. So you need a pretty stable baseline in terms of photometry, the brightness of the star, if you were to see very little dip in its light curve to find the planets, like transit method, but it is simply impossible. So what that means is that the bottom line is that we cannot use the techniques we have developed for exoplanet detection, and we need to develop new techniques if we were to find forming planets. So the question is then, what could it be, right? So one way is to look at the footprints left on protoplanetary disks by protoplanets. So this is a movie where I add a planet. So star is at the center, and this is 3D hydro simulation with volume rendering. Here's the planet, and you are looking at the density of the disk. Don't worry about the exact numbers. It's yellow is high density, purple is lower density in log scale. But what you see is that if you have a planet, you open a gap around its orbit, it clears its orbit, right? And also you can see this spiral arm excited by the planet in the outer disk as well as in the inner disk. So those are a very large global scale feature. So the planet itself is very, very small. It's even smaller than the size of the star, of course. But these features, the gap, for example, it can be as wide as 10 to about 50% of the semi-major of the planet. So it's very large scale structure. And also these spirals, if you see this spiral wave, they propagate all the way to the inner disk and the outer disk until they dissipate. So the point here is that planets leave footprints that are much larger than the planet itself, which is great. And we can try to observe these planet-disk interaction signposts. So when let's say we observe a gap or a spiral, right? What we can do then is that, okay, this is a paper that I have worked with a PhD student that I have been mentoring. So what he has done is to run a parameter study varying the disk conditions like disk temperature, disk viscosity, and planet mass. And what this plot here shows is basically as you grow planet mass, the depth of the gap becomes deeper, which makes perfect sense. And this is another plot where he made for the width of the gap now as a function of mass, and you see a certain trend. So if you observe the gap, if you can measure the gap width and depth, then you can try to infer the mass of the planet. And you can do the same thing for the spiral. This is now a varying disk temperature and planet mass. And spirals look different in terms of their pitch angle, how open they are open or how tightly they are wound, and the number of spirals and spacing between spirals. So we can try to use these empirical relations to infer the planet mass. But how can we observe these signposts, right? We need a high spatial resolution, first of all, to image these AU scale features in disks located far away beyond 400 light years. So the diffraction limited resolution, angular resolution data here is observing wavelengths divided by the diameter of the telescope. So if we wanted to observe AU scale features at 400 light year, that is about 0.02 arc second. And we are going to use 1 millimeter because we want to see through the nebula gas and dust, and we want longer wavelengths to avoid any extinction. And the diameter of the telescope we need is 10 kilometers, which is pretty big, right? Now, it's not just big, but it's expensive. This is an interesting paper written in 1987, titled A Cost-Performance Model for Ground-Based Optical Communications Receiving Telescopes. What they have done is basically they looked at the cost required to build different telescopes. For example, these ones are space telescope. Hubble Space Telescope is here as a function of optical diameter of those telescopes. So if you look at this space telescope, optical telescope, and these are radio telescope, here's 3LA, and radio telescopes, they are the cheapest ones, right, at a given diameter. But this is 1 meter, 10 meter, 100 meter, a kilometer, and we need 10 kilometers, right? So if I just wanted to extrapolate, I found that this scales like cost proportional to the diameter to the cube. So if I go all the way to 10 kilometers, what that tells me is that we need $10 trillion US dollars in 85 or $29 trillion in 2021. So it's just impossible to build such a huge antenna or telescope. But astronomers are smart and physicists as well. So what we do is we use this thing called interferometer. And ALMA is a radio interferometer. So what it is that instead of building a single dish telescope that has a diameter of 10 kilometers, what you do is you build small telescopes and space them across 10 kilometers. And by doing so, you can effectively have a single dish telescope that has aperture of about 10 kilometers. And this is my favorite movie of ALMA. They are looking at the night sky down in Chile, in Atacama Desert. So one of the very first protoplanetary disks they observed with ALMA is this object HL tau. So this is not the HL tau image, but this is an image taken with KARMA. This is a previous generation radio interferometer, and this is taken at 1 millimeter wavelengths. So the star is at the very center, and here's some continuum coming from the surrounding disk. So we knew that there's something there, but this is what ALMA has given us. So we now see a lot of structures in this disk, a lot of rings and gaps, these fine scale structures, and this is taken at the same wavelengths to the KARMA data. And when people looked at other disks, which we know that there are not, great structures, outstanding structures at lower resolution, right? This is a survey done with ALMA, and we see these substructures, rings and gaps, and sometimes vortex-like asymmetry, spirals. We see this everywhere, right? This is another example where we see spirals, a collection of 9 disks with spirals. So this is great because it's very promising that we see gaps and spirals, the structures we know planets can create. But where are planets in this disk? Because we don't see the planet themselves directly, right? And how convincingly and unambiguously can you connect planets to these substructures? Right? So for example, this is an object called MWC758. It has 2-armed spirals, right? And if you have this object, where should we put a planet or planets to reproduce this observation? Do we need 2 planets for each spiral, or do we need just 1? If one, where, for which one, right? Do we need to put planets in outward of the the spirals, or inward of the spirals, right? To answer all these questions and remove the degeneracy, right? We really need a solid theoretical framework on planet disk interaction. But I noticed that our theoretical understanding was incomplete. Even the formation mechanism of spirals was not fully understood. So one of the things that have long been seen in planet disk interaction simulations is this phenomenon that one planet can excite multiple spirals. This is one example that I showed earlier. Like you see a planet in this case is right here outside of the box. It creates a spiral here and the other spiral here, so two spirals. And this one is another one of the oldest literature I could find from 1979, where the authors ran a simulation with a central star and a companion here. Star is here, and companion drives two-armed spirals, pretty similar feature qualitatively. So whenever you run planet disk interaction simulations, planets excite multiple spirals, and that's the most fundamental thing that happens. But we didn't really have the answer why it happens. And as a theorist, this really bothered me because we don't understand why this is happening and what's going on. So I tried to look at the equations to see if I can explain this. And to explain how one planet can launch multiple spiral arms, I will have to show you some equations. Those might not be as pretty as the images that I showed, but this is a crucial part in understanding the basics of planet disk interaction. So I'll go with that for the next few minutes. But I can tell you that the physics I have here is only gravity. And I assume that it's pretty much, probably much simpler than the physics you have for your research. So let's get started. So here's my planet, and you can draw radius vectors, rp to the planet, r to an arbitrary position in the disk, and this position between this position and the planet, you can make r minus rp vector. Now, at this position in the disk, what you can do is you can write down the potential, gravitational potential felt by the planet, which is simply minus gmp, where g is the gravitational constant, mp is the planet mass, divided by the distance, right? But what I will do is to try to express this gravitational potential with Fourier series. This is radial component, and this is the azimuthal component. And by choosing appropriate amplitude, you can make these two the same, right? So I just expanded that potential. So as I said, I am a theorist and I run numerical simulations. So what I decided to do is I put a single potential term. So in this case, m equals 2 term. So phi 2r cosine 2 phi, instead of putting all the potential, the full potential. So this is what happened. So because I put phi to r, this is dependent only on the radius. So what you expect to see is axis symmetric feature, axis symmetric perturbation that has m equals 2 symmetry. And this is what you see. Here's one spiral, and here's the other spiral. And I can do the same for m equals 3, and you see 3 spirals. And m equals 4, you see 4 spirals. M equals 5, you see 5 spirals, right? But this is not something new, actually. This is already known since 1970s from this seminal paper, where they showed analytically that M Fourier component of the planet's potential can excite M axis symmetrical spiral wave modes at the Lindeblad resonance. What I've done here is that I just visualized this statement using numerical simulation. But what I have done in addition to this is that now what I'm going to plot here is all the n equals 0 component. So this one here from m equals 2 mode, and this one from m equals 3 mode, this one from m equals 4, and this one from m equals 5. So when I did that, this is m equals 2, 3, 4, 5, all the way to m equals 20. And what you will see is that, except probably for a couple of two very initial modes, azimuthal mode, you will see that they are overlapping in space in azimuths very well, which means that if you were to sum them all, right, we Fourier transformed, right? Now we express the full potential with Fourier series. So if we sum them up, they will add up together to make a coherent feature through constructive interference, right? I can do the same for n equals 1 component, this one, this one, this one, this one, and they start from from farther away in azimuth, but as they propagate inward, they again collect in a narrow azimuthal angle, which means that they can form another spiral. You can do the same for n equals 2 component, and this is what happens. M equals 3, 4, all the way to 20. They will have to propagate more because they start from further away in azimuth. But the point here is that the propagation of these waves are such that they can collect as they propagate. So constructive interference among these different azimuthal wave mode, they can collect to form coherent structure, which forms spiral waves, spiral arms. So now what I have done here is on the right-hand side, I ran the simulation with the full potential minus gm over the distance. So planet is here, you form this primary spiral arm and the secondary and tertiary. And when I sum up all the previous, if you look at the previous slide, I did a Fourier component m equals 2 to 20. And I add them up linearly, right? And when I did that all the way up to m equals 30 mode, we end up with the same density distribution, which is reassuring that this theory of constructive interference can explain multiple spiral arm formation. So some of you may want to ask that, well, this doesn't look like, you know, the observation, the spiral look very different, right? So why is it? That is probably because of the mass. So I wanted to use linear theory. So I used very low mass planet, but as you increase the planet mass, the spirals generate stronger shock, which means that they propagate faster. So they tend to appear more open in morphology. So if I rotate and flip this 10 Jupiter mass planet case, you see pretty much similar morphology to this observation. So this is great. Now we understand why one planet can excite multiple spiral arms, but what can a spiral arm do physically, right? We already know that spirals can transport angular momentum as it shocks the disk gas, and that's how a planet opens a gap. The outer spiral arm and inner spiral arm, they shock the disk gas and they clear up the vicinity of the planet. Now, the question is then that what happens when a planet excites multiple spiral arms? And the answer is simple. The planet can open multiple gaps, right? So this is a simulation, again, planet disk interaction simulation, where I have a planet here and you are looking at the surface density of the disk. And you can see that in addition to the main gap around the planet's orbit, you see this high density region with red, lower density region, high density region. So you see 1, 2, 3 gap in the disk. And why that happens is that the planet generates secondary spiral at this location, tertiary spiral at this location, and they open a gap at each location. So in addition to this hydro simulation where I have only gas, I added dust grains and see how they evolved. And finally, this is the continuum image based on grain plus gas calculation. And you can see that you can open a gap, but also you can open additional gaps in the inner disk, multiple rings and gaps. And in fact, this is the survey that I mentioned earlier, D-sharp survey. This is the actual observation of a disk called AS209. You see one broad gap, and then smaller gaps in the inner disk. And the authors here ran numerical simulation with just one planet in this outermost gap, and they could explain all these inner gaps using just one planet. So the bottom line here is that the number of observed gaps is not necessarily the same as the number of planets. If you see 3 gaps from your observation, right, the easiest way to interpret that is that you have 3 planets, right, 1 in each gap, but then may not be necessarily the case. So that's a problem, right? we want to see the planet and we want to know where the planet is in those disks, but we cannot really tell that from these observations. So what we really need is that we need localized direct evidence of planets. So some of the examples include thermal emission from the planet. This is a figure I showed earlier. When you have a star, you see black body spectral energy distribution. When you have a planet, you expect the same, but planets are cooler than stars, so at longer wavelengths and less brightness. Planets can have circumplanetary disks. Those are analogous to protoplanetary disks around stars. They can have their tiny disk around themselves. And we can expect that if planets accrete some material from their circumplanetary disk, and they can generate some shock on their surface, photosphere. So you can expect accretion shocks, and we can trace those shocks using, for example, H alpha. This is hydrogen line. And there's this perfect case study, PDS-70, where all of those three, near infrared thermal emission, H alpha line emission, and millimeter continuum, all of them are observed. So brief bio for those who are interested in. And the star hosts a transition disk. And what transition disk is that those are the disks having big cavity, big inner cavity in dust continuum like this one. PDS-70 is this one. So you see one ring, but there's a big cavity here. And a compelling idea to explain this kind of morphology as opposed to multiple rings and gaps like in HL tau is that the system must have multiple giant planets or single giant, but that's very massive, or even a stellar companion. So something special must be going on in these transitional disks. And indeed, in 2018, a team has discovered and reported PDS-70b, a planet in the disk. So if you look at this part of the disk, this is taken at infrared wavelength, and you are looking at thermal emission coming from the planet. You consistently see this white dot at the same location. And some of you may be skeptical about all these speckles, but when you look at this image where they spent 2.5 hours of integration on that system, you see the ring and a big cavity in the middle, and you clearly see this dot here. This is a planet. Again, we are looking at thermal emission coming from this giant planet. And another group observed this system looking for H alpha emission, and they detected H alpha emission at the location of the B. And by looking at the accretion luminosity, you can then estimate how much material, how fast they are accreting. And this is the number that they reported, 10 to the minus 8 Jupiter masses per year. So our team has asked ARMA observation to this disk. This is some specifics for those who might be interested in. So this is what we got. So on the left is the CO emission integrated intensity on the sky, projected on the sky. So you are basically looking at the gas distribution around the star, which is at the center. On the right-hand side, what you see is dust continuum. So you are looking at basically grains with sizes of about millimeter, right? And you see this big cavity here. One question that we had was, if you overplot the orbit of PDS-70b, right, this dashed ellipse, and this is the contour that shows the continuum observation, there's a big region between the orbit of the planet and the peak of the continuum. And there's some non-zero emission coming from the cavity, inside the cavity between the orbit of the planet and the ring, continuum ring. And this is something I run numerical simulations, but this is something that we typically don't see. And I ran a lot of numerical simulations to reproduce this particular morphology of the disk. And I ended up, giving up because I was just not able to do that. So this is actual last sentence of the paper we published in 2019. So what we said there is that we find that even a planet with a mass of 10 Jupiter masses may not be sufficient to explain the extent of the wide gap. And an additional low mass companion may be needed to account for the observed disk morphology. And it turned out that PDS-B is not alone. There's another planet. Actually, it was in the original discovery paper, this one here. It was on and off. So in that paper, they claimed that it could be this feature, the protoplanetary disk, not a planet, but it turned out this is real. Again, this is H alpha observation. You see H alpha emission at the location of the B, and also at this location C. And this is a paper led by Andrea. He looked the data carefully, the continuum data, and found millimeter continuum coming from C and something tentative around B. So this is really great. We directly detected 2 planets in one system. And as a theorist, I decided to run numerical simulations to learn about the system more, because it is great that we know where the planets are and we roughly know what the masses are. So this is the simulation. Again, you are looking at the surface density distribution or gas density, and the 2 planets open a big cavity in the inner disk. And on the right-hand side, what you see is the semi-major axis of the 2 planets, the B and C. And this one here, down right, is the resonance angle. That's for 2-to-1 mean motion resonance. So what that means is that over the time, the inner planet orbits around the star twice, the outer one orbits the star once. That's mean motion resonance. And when they are in mean motion resonance, this angle is supposed to be liberating around 0, which is happening right now, right? So we know that those 2 planets are in mean motion resonance. Well, the simulation suggests that they are in stable orbital configuration. So this is another plot showing that the period ratio of the two planets, so it's close to 2-to-1, but it's slightly larger than 2-to-1, and that is because you have these spirals from those 2 planets, and they keep each other, so they prohibit those planets to become within exact 2-to-1 mean motion resonance. So it's slightly larger than 2-to-1. And the other thing we found here is the orbital eccentricity of the inner planet can be quite large, in this case 0.07, whereas the outer planet remains nearly circular. And this is really exciting paper that came out earlier this year by Wang et al. They looked at this system with VLTI. This is interferometer at microwave lengths, infrared, and they looked at they collected the data from literature, so the position of B and position of C, and they collected their data points with extreme precision. And when they feed those 2 orbits, the blue is for PDS-70b, the inner one, and the outer one, what they found is that the period ratio is about 2.13. So this is consistent with the fact that they might be in 2-to-1 mean motion resonance. And although the error is pretty large, but they suggest that it can be a little bit larger than 2-to-1 mean motion resonance. So there's one. And circular orbit is disfavored for PDS-70b. B has pretty large eccentricity, as you can already see from here on the left panel. And C's orbit is consistent with a circular orbit. So this is all consistent with the simulation that I ran for the 2019 paper. So this is really exciting. And also what is exciting is that if you look at this specific motor exoplanet system, HL 8799, you have the star at the center, and you see 4 dots here orbiting around the star. Those are giant planets in the system, and they are in a chain of 2-to-1 mean motion resonance, so 8-to-4 to 2-to-1 mean motion resonance. So it is also consistent that giant planets might be forming in mean motion resonance. And we have some evidence in our solar system as well that Jupiter and Saturn might have formed in mean motion resonance. So this is a famous grand tech model, which is built to explain the small mass of the Mars. So the idea is that Jupiter migrate into about 1.5 a year to cut the inner disk, and then Saturn followed, migrated in and locked in 3-to-2 mean motion resonance. And when that happens, those 2 migrate outward to the current location. So we have some evidence of that, and it is also consistent with PDS-70 that giant planets might form in mean motion resonance. The second thing we can learn is the particle trapping and filtration. So what I have done here in this simulation is that I added particles with different sizes from millimeter, 100 micrometer, 10 micrometer, 1 micrometer, 0.1 micrometer with different colors. And large grains, again, they are collected within pressure bump. But if you look at the inner disk, what you see is only green and dark blue particles, which is basically very small 0.1 micrometer size particles because they are following the gas and flow in. And all the large grains are collected in the outer disk. So this is consistent with the observation. And this is, again, if we compare exoplanet with exoplanetary system, uh, you see a lot of population here, which we call super Earth or mini Neptune. They are within Earth orbits, but they are pretty big in mass, usually 10 to 20 Earth masses. And we now know that more than 30% of sun-like stars have at least one such a planet. And the question is then, why do we not have such a planet? Why did we fail to become a super Earth or mini Neptune? One possibility is that Jupiter and Saturn has grown up large before we grew up. So we basically have started with solid material because Jupiter and Saturn blocked all the material beyond their orbit. And again, there's some potential meteoritic evidence that Jupiter has formed early, within about 1,000,000 years, tracking large grains beyond its orbit. So it's really the moment when theory and observation meet and they collaborate with each other. In 2018, PDS-70b was discovered. In 2019, we said that there might be a low mass companion, additional companion. And then in the same year, another group found PDS-70c. And then we proposed that those two planets might be in mid-motion resonance. And earlier this year, another observing team found that they might be, well, the data is consistent with 2-to-1 mid-motion resonance. So this is really exciting moment, and fast turnaround between observations and theories. So it's really exciting moment in time. There's that. So I guess I will close up right now. So I will briefly mention, like in a couple of minutes, what is our future, right? So I showed a lot of data and theories and numerical simulations, but what we need now is to develop and improve protoplanet detection techniques. For example, transit and radial velocity that used for a mature exoplanet detection. We need something like that with some strong theoretical background. So we need to build solid theoretical frameworks with which we can properly interpret those observations and eventually quantify protoplanet properties like mass and radius and density, etc. So one thing I'd like to highlight is that we may need to probe the gas component of the protoplanetary disk because they contain most of the mass, right? So this is one example. You can try to search for some kinematic evidence. This is actual observation of HD 16396. You see this kink feature here in the observation. You are looking at CO emission. And when there's no planet, you just expect to see a smooth feature butterfly pattern. But when there's a planet here, you put a planet, the spiral perturbs the gas velocity and you see this kink. So this is great because now you can pinpoint where the planet might be in the disk. And this is another example. You can start to look at the kinematics of the disk gas. So this is inferred velocity vectors at 12 CO emission surface. So you look at this falling down meridional flows at these 3 locations. By the way, these locations are where we see the gaps in continuum, and we see this kink in the disk. And what we think is that there's planet down there, so pushing away materials, trying to open a gap. And near the surface, the disk tries to recover its form, its density. So we expect meridional flows, and this is a simulation that I ran to explain the observation. You can see that there are 3 planets. And if you look at the surface, there's this downward motion, meridional flows at these 3 locations. This is a zoom-in version. So this is, again, where theories confront the observation. This is great. Okay, and we can expect synergy with upcoming space missions. This is expectation simulated observation for the same object, HD 16396 with James Webb Telescope. We can easily detect a planet with 2 Jupiter masses, which is predicted for the disk, for the system. We can even go down to half the Jupiter masses. And in long term, we will be able to peer into the terrestrial planet forming regions using extremely large telescope and also NGVLA to answer how terrestrial planets might form. So I went a little bit long, but this is my summary slide. I wouldn't mind if you forget what I told you about, how planet launches multiple spirals, how one planet can create multiple gaps, whether or not giant planets forming in motion resonance. You are fine to forget about all the details, but what I'd like you to remember though, after my talk, and I hope I convinced you today, is that right now and the forthcoming decades are really special and exciting moment in time to study protoplanetary disks and planet formation. We are now able to observe planets in formation, and we see all these substructures, which are promising evidence of the presence of planets embedded in the disk. And our futures are bright with all these missions and observing facility. I am very confident that we can have this synergy between observation and theory. And one day, perhaps 30 years from now, February 10th in 2051, I'm hoping that I can present a figure like this one and show how much progress we have been made as a field over 30 years. We have just started this journey, right? We discovered the first protoplanet PDS-70b in 2018. And again, I'm confident and positive that an exciting journey is awaiting us. So I have listed a few techniques we have started using or started developing to detect protoplanets here. And I'm really excited to see what brilliant ideas we will come up with in the future as new observing facility becomes available. So with that, I'll stop and take any questions. Thank you.
Thank you very much, Jaehan. I'm gonna clap for everybody. Very nice presentation, very nice talk. So